Welcome to the Deep Dive. Today, we're getting into something that sits right at the intersection of some really high-stakes engineering and, cutting-edge data science.
It's a fascinating space.
It is. We're looking at how researchers are figuring out how to reliably predict the fracture strength of critical materials, specifically polycarbonate.
And for anyone who designs anything that has to carry a serious load, from a tiny medical device to a big aerospace part, polycarbonate or PC, is just a staple.
Right.
It's a high-performance thermoplastic. It's known for its amazing mechanical strength and just this incredible ability to resist impact. You really do see it everywhere.
And that's exactly why its reliability is, it's non-negotiable. But here's the challenge that engineers always face. Real components, they always have geometrical discontinuities.
Yeah.
Notches, corners, tiny imperfections from manufacturing.
And those features, they act as stress concentrators. They focus the force.
So what happens then?
Well, when you're dealing with a material like PC, which is ductile, meaning it bends and stretches a lot before it breaks, your traditional, simple analytical methods often just fall short.
They can't predict when it's actually going to fail.
Exactly. They have a really tough time predicting when and how that component will finally fracture under load.
Okay, so if the old methods are unreliable, and we know that just, smashing hundreds of parts in a lab is super slow and incredibly expensive, what's the more elegant solution this research is proposing?
The elegant solution is this hybrid approach. The core idea is, look, don't rely only on expensive physical tests and don't rely only on basic equations.
You combine them.
You combine them. You create high-fidelity synthetic data, and you generate that from a physics-based simulation that you've already rigorously validated.
And you use that data to train an AI.
You use that synthetic data to train and augment a powerful machine learning model. You're basically teaching the AI the rules of physics without having to physically break a single thing.
Okay, let's unpack that, starting with the physics foundation. Because before they could trust any of the simulated data, they had to prove their model was sound.
Absolutely.
They chose to anchor it in something called the theory of critical distances, or TCD, specifically the point method. For those who aren't familiar, what makes that a good starting point?
TCD-PM is popular because it strikes a great balance. It's much more accurate than the simple formulas, but it avoids the intense computational cost of really complex constitutive models.
It's a practical middle ground.
It's an efficient middle ground. And the theory simplifies the fracture process in a really clever way.
Yeah.
It doesn't assume failure happens at the very, very tip of the notch where the stress is highest.
Okay, so where does it assume failure happens?
It suggests that fracture occurs when the stress at a very specific location, what they call the critical distance, L/2, reaches a critical failure stress.
The material's inherent strength.
The inherent strength, sigma 0. So you're basically looking just a little ways away from that sharp corner. And if the stress there hits a certain limit, the whole thing fails.
So this method boils the whole complex process of failure down to just two core material constants.
That's it. The inherent strength and that critical distance.
And for this specific polycarbonate, what values did the researchers find?
They pinned them down very precisely. The critical distance, that L/2 value, was 6.95 millimeters.
Okay, 6.95 millimeter.
And the inherent strength, sigma 0, was determined to be 54.5 megapascals. These two numbers, they're the absolute bedrock of the whole study.
Right, they translate the physics into numbers the simulation can use.
Exactly.
Now, to ground this in reality, they needed real data. They used U-notched specimens and put them under a slow quasi-static load. How comprehensive was the physical testing?
It was very targeted. They didn't test hundreds of specimens. They tested 11 distinct geometrical setups, and each one was tested multiple times to make sure the results were reproducible.
And they varied the geometry.
Oh, significantly. The notch depths went from 4 millimeters up to 7, and the notch radii, how sharp or blunt the U-shape was, varied from 1.5 all the way up to 5 millimeters.
So they got a good range of shapes.
That diversity was absolutely essential. The goal is to predict failure across all kinds of different designs, not just one.
Yeah, here's the technical point that I think is really important. Polycarbonate is tough, it's ductile, it stretches, yields.
It has elastic plastic behavior, yes.
But the model they use, the TCD-PM, it relies on an assumption of linear elasticity, the simplest kind of material behavior.
Right.
That sounds like a dangerous oversimplification for a ductile part. How did they justify using that simple model in their finite element analysis?
That is the pivotal question, and it's really the key decision point that makes this whole thing work. They were very careful. They did not try to predict the final catastrophic rupture of the part.
Okay, so what did they define as failure?
They pegged the moment of failure to the initiation of necking.
Necking being that point where the material kind of thins out in one spot just before it snaps.
Precisely. They measured the average stress when necking began at 66 megapascals. And they reasoned correctly that at that exact moment, the local stress field right around that critical distance is still behaving well enough.
It hasn't gone completely haywire yet.
It hasn't. It can still be accurately approximated using a simple linear elastic model. So they use standard elastic numbers. Young's modulus of 2267.6 MPa and a Poisson's ratio of 0.38.
It's a really smart intellectual pivot. Simplify the model by being very precise about what you're calling failure.
That's the key.
And the proof is in the pudding. Did this simplified physics model actually match their real-world tests?
It was an overwhelming success. And that's why this research is so impactful. They ran the simulations using those TCD-PM constants, the 6.95 millimeters and 54.5 MPa, to predict the fracture loads.
For all 11 of their physical test setups?
Yes. And when they compared those theoretical loads to the actual physical loads they recorded in the lab, the deviation was just, incredibly small.
How small?
It ranged only from a negative 3.48% to a maximum of 4.40%.
Wow. That's really close.
It's near perfect alignment, and that's what validates their simulation. It proves it's a highly reliable predictor of fracture load for this material in this kind of geometry.
And that validation is the permission slip, right? Once your simulation can predict failure with less than 5% error, you don't need to keep breaking plastic.
You don't.
Which transitions us perfectly into the data science side of things. The goal now is to train a machine learning model, XGBoost in this case, to learn this relationship without needing so many real-world tests.
That's precisely right. Since the simulation was proven to be such an excellent oracle, the researchers then used that same framework to generate their synthetic data set.
So they just ran it more times.
They created 32 brand new high-fidelity data points by simulating geometries that were different from the original 11 experimental ones.
Which saved them the time and money of actually making and testing 32 more physical parts?
A huge savings.
So in the simulation, how does it know what the fracture load is for these new synthetic points? What is it measuring?
It's just waiting for the physics equation to be satisfied. The simulation increases the load step by step, sometimes by just 1 Newton, and it's constantly monitoring the stress.
At that critical distance.
At that 6.95 millimeter mark. The instant the maximum principal stress there hits the inherent strength of 54.5 MPa, that lobe step is recorded as the fracture load.
And that gives them these 32 perfectly clean, deterministic data points.
Linking geometry directly to the predicted fracture load.
This brings us to the really fascinating part of the research, the experiment design. Because they didn't just dump all this synthetic data in with their real data.
No, they were very systematic. They designed 6 distinct training compositions to really evaluate the power of augmentation versus, say, substitution.
Okay, so how did that work?
They set aside the original 11 experimental points as the fixed final test set. All 6 models they built had to predict the outcome for those 11 real-world parts.
And the training data was what changed each time.
Exactly. For the first 5 scenarios, they kept the training size constant at 22 points, but they systematically replaced real experimental points with synthetic ones.
So you had the baseline model, which was only trained on 22 real points.
That's your control group.
Then you had the hybrid compositions, like 50-50 experimental and synthetic. They were testing the idea. Can this clean simulation data replace messy, expensive, real-world data?
That was the core question. And then the final critical test was the full dataset model.
Which was just everything.
Everything they had.
Yeah.
All 22 real experimental training points, plus all 32 of the new synthetic points. A total of 54 training points.
And they kept the machine learning setup, the XGBoost configuration, the same for every test to make it a fair comparison.
Right. 500 estimators, low learning rate, fixed tree depth, all to isolate the effect of the data itself.
Okay, this is where it gets really instructive. Let's look at the numbers. Specifically, mean absolute percentage error, or MAPE, and the R-squared value.
Right, which tells you how well the model can generalize to new data.
What did that baseline model, the one trained only on real experiments, show?
The baseline set a really solid standard. It had a MAPE of 1.23%. So its predictions were, on average, just over 1% off from the actual fracture loads.
That's pretty good for an engineering application.
Very good. And its R-squared score was 0.757. a respectable starting point.
Now, what happened when they started replacing that real data with the mathematically perfect synthetic data?
Performance got worse immediately. And this is the first crucial insight for anyone thinking about this kind of hybrid modeling.
As they swapped real data for synthetic data, the models lost their ability to generalize.
They did. For instance, the model that was half experimental and half synthetic saw its MAPE jumped up to 2.29%.
That feels so counterintuitive. If the synthetic data comes from a model that you've proven is 98% accurate, shouldn't adding more of that perfect data make the machine learning model smarter?
It makes it smarter about the physics, but it makes it less robust when it sees the real world. A machine learning model like XGBoost, it learns not just the pattern, but the variability within the pattern. That noise from the real experiments, the tiny differences in manufacturing, the subtle material scatter, that's actually a valuable feature.
It's information.
It's crucial information. When you replace that real-world messiness with deterministic, mathematically perfect simulation data, you're starving the model of the very information it needs to handle a real component.
So it basically overfits to the perfection of the simulated world. What about the ultimate test of that idea? The model trained only on synthetic data.
That one was the worst performer by far on the real test data.
I'm not surprised now.
It had the highest MAPE at 2.86%, and its R-squared score just plummeted to 0.216. The model perfectly understood the pristine world of the simulation, but the moment it was exposed to the normal physical scatter of those 11 real test parts, it failed. Catastrophically.
So that's the big takeaway right there. For safety-critical engineering, you can't fully substitute real-world testing with simulation alone. You need that physical grounding.
You absolutely need it.
Which brings us to the winner. The best strategy wasn't replacement, it was augmentation. Tell us about that full dataset model, the one that combined all the data.
This combination model really showed the power of doing this the right way. It achieved the best overall results because it was leveraging the strengths of both kinds of data.
So the synthetic data provides volume and knowledge of the physics?
And the real data provides the necessary context about noise and real-world variability. This full model actually surpassed the original experimental-only baseline.
By how much?
It achieved the lowest mean absolute percentage error of the entire study, dropping down to 1.18%. Its mean absolute error was just 78.73 newtons.
That's impressive.
And its predictions against the actual experimental lows, they ranged only between negative 4.14% and a positive 2.59%. And crucially, it maintained that high R-squared value. It was just as robust.
So the synthetic data didn't muddy the waters. It sort of smoothed out the decision boundaries for the model, giving it higher confidence across geometries it had never physically seen. This is a massive gain in efficiency.
That is the key takeaway. This research provides a clear pathway for engineers working with these high-performance plastics. You can reliably predict fracture loads for these complex notched components.
You establish the physics, validate your model with a small set of real tests.
And then you use that validated model to simulate hundreds of variations, augmenting your real data. You slash your testing time and cost, and you simultaneously improve the robustness and the accuracy of your final predictive tool.
We've seen a really powerful demonstration here of machine learning not replacing mechanical analysis, but learning the patterns established by validated physics.
And then using the real-world data to capture that critical variability it needs to generalize successfully. The ability of this validated physics model to generate meaningful synthetic data, which then enhances XGBoost, is a major step forward for materials informatics.
It shifts the focus.
It really does. It shifts it from brute force experimentation to smart integrated modeling.
And yet that failure of the purely synthetic model, that remains a pretty potent warning.
It absolutely does. This study shows that augmentation works brilliantly within the boundaries they tested, where the physics is well understood. But for you, the listener, especially if you're designing safety-critical components, things where failure is catastrophic, the question is still open.
Right.
Since we know the purely synthetic model was useless for generalization, how much minimal experimental data is truly required to capture that real-world variability? Enough to ensure your hybrid model can safely and reliably generalize across entirely new material batches or new manufacturing processes or geometries that fall way outside your initial training set. That minimum requirement for real-world truth, that's perhaps the next great frontier in this kind of hybrid engineering.